Hey folks, in this short video, we are going to look at our Pythagorean identities, which are a really common type of identity. I'm going to assume that you've already watched my video over reciprocal and quotient identities, but we're going to do kind of derive the Pythagorean identities. There's three of them, and then we're going to use those to do three problems that might be kind of like what you'll see on a homework quiz or test, and we'll do those at the end of the video. So starting off, you might have looked at your context clues and thought, oh, Pythagorean, maybe it has something to do with the Pythagorean theorem. And so, yeah, let's think of it that way. So if I have a given angle theta, we could define our sides as A, B, and C. And we know that by the Pythagorean theorem that A squared plus B squared equals C squared. And from a given angle theta, when we moved on to trig, we started calling those opposite, adjacent, and hypotenuse. So instead of A squared plus B squared equals C squared, we would say opposite squared plus adjacent squared equals hypotenuse squared. Now, where we go with the Pythagorean identities, though, is what if I divided all three of these terms or both sides of my equation by the hypotenuse squared? And now you're thinking, oh, opposite over hypotenuse, adjacent over hypotenuse. These look like some of our trigonometric ratios, and they are. If I have something squared over something squared, it could be rewritten like this. And then lastly, opposite over hypotenuse is sine. Adjacent over hypotenuse is cosine, and hypotenuse over hypotenuse is 1. So what we find is this is our most basic Pythagorean identity. Sine squared theta plus cosine squared theta equals 1. So let's start with that. That's our first Pythagorean identity. And what we're going to do to derive our other two is we're just going to take it and we're going to do some algebra to that identity. So if I start with my original Pythagorean identity and divide both sides of the equation by sine squared theta, we're going to get this will simplify, this will simplify, and this will simplify. First, this simplifies to just a good old 1. Then cosine over sine, or cosine squared over sine squared, is cotangent squared. And then the reciprocal of sine, 1 over sine squared, is cosecant squared. So here's your second Pythagorean identity. And then let's come over here and let's take our same original Pythagorean identity, and now instead of dividing by sine on both sides, let's divide by cosine on both sides. So I'm going to divide by cosine on both sides. Sine over cosine is tangent. Cosine over cosine is 1. And 1 over cosine is secant. And all of those values are squared. So here's our original Pythagorean identity. And then we used it to derive our third Pythagorean identity. Or our second and third Pythagorean identity. So here are your three Pythagorean identities. We need to have these written down. I won't say you need to memorize them because most of the time you'll have an identities chart. But one thing you want to be kind of aware of is sometimes you might be using this form of the identity, but you also might be using an algebraic manipulation of it. And what I mean by that is if I start with sine squared theta plus cosine squared theta equals 1, hypothetically, I could subtract cosine squared theta from each side of this and have sine squared theta equals 1 minus cosine squared theta. So if you see an expression that looks like this, you might need to substitute it out for sine squared theta. So you might be using some manipulation of each of these as well. But the more problems you do, the better you'll get at it. So let's jump into our three example problems. So on this first one, we have sine squared alpha plus cotangent squared alpha equals cosine squared alpha. It doesn't matter if we use alpha or theta or whatever for our angle. We're using alpha in this problem. But what I see when I look at this is I see a sine squared theta plus a cosine squared theta. And if I look up here, we know that sine squared theta plus cosine squared theta equals 1. So, I mean, if you wanted to, we could rearrange first. So I just kind of rewrote this in a different order, but we know that sine squared plus cosine squared equals 1. So I substitute in a 1 for that. And then we have cotangent squared alpha that we just bring down. Well, then you're looking at your identities thinking, oh, 1 plus cotangent squared alpha, that looks familiar. That's the same thing as cosecant squared alpha. So I'm going to take that and substitute in cosecant squared alpha. And that's as simple as this expression gets. So for this first one, we took this big complicated expression and find that with our Pythagorean identities, it simplifies down to a nice simple cosecant squared alpha. Let's do example 2. So right here we have cosine theta over 1 minus sine theta and then minus tan theta. Now, tough part about this one is you're looking at it and you go, there's nothing squared. How are we supposed to use our Pythagorean identities, but let's do some algebra and let's see where we get. So I'm going to start, I'm going to kind of copy down this part, but then we know tangent theta is equal to sine theta over cosine theta. We know that because that's our quotient identity. Now, if I'm actually subtracting these, we need to get a common denominator. And if I look at my fraction on the left, what it's missing is it doesn't have a cosine theta on it. So I'm going to multiply by cosine theta over cosine theta. And then this fraction, it doesn't have the 1 minus sine theta in its denominator. So I'm going to multiply by 1 minus sine theta over 1 minus sine theta. And whenever we're looking at this, I'm going to kind of do some simplification here. This numerator is going to become cosine squared theta. And then we have minus sine theta times 1 minus sine theta. But I can write this all over one denominator because our denominator is the same. Our denominator is going to be cosine theta times 1 minus sine theta. Now, my next thing I'm going to do is I kind of want to simplify this part right here. I kind of want to distribute. So if I distribute a negative sine theta into both of those, then we'd still have my cosine squared theta, but then negative sine theta times 1 is just minus sine theta, and then negative sine theta times negative sine theta, a negative times a negative is a positive, and sine theta times sine theta is sine squared theta. So then we have our denominator is still there. And what I see next is, like our previous problem, and you'll get better identifying this the more of these that you do. You see that we have sine squared theta plus cosine squared theta? That looks like our original Pythagorean identity up here. So I'm going to copy it up here, but instead of that part that I've highlighted in orange, I just am going to substitute a 1 in for it. And then we still have our minus sine theta from right here. And then we're just going to copy down our denominator, cosine theta times 1 minus sine theta. Well, now that I'm looking at this, it looks like I have a 1 minus sine theta in the numerator and a 1 minus sine theta in the denominator. That is going to cancel with that. And in the numerator, all we'd be left with is a 1. And my denominator would be left with a cosine of theta. And this is pretty well simplified, but it's technically more simplified if I go ahead and use my reciprocal identity to turn that into secant theta. Okay? Now, and let's do our last question. Here's our example 3. And this one is going to get a little bit hairy, so instead of me writing it out, I've just kind of typed it out. So if we start with this value being squared, we know that any value squared, oops, got to back it up, is just that value times itself. So this sine beta minus cosine beta squared is sine beta minus cosine beta times sine beta minus cosine beta. Then my plus sign, and then the second expression is expanded. Now, what's kind of gross with these is with both of these, you're going to have to FOIL it out. So sine beta times sine beta is sine squared beta. This, and then you're going to do the same thing over here. Now, since it's not really the goal of this video, I'm not going to walk through all that. But here's what you should end up with once you expand that, okay? These two right here become this, and these two right here become this. Now, I've still got the parentheses, but they're not really necessary anymore because I'm just going to add these. And so I have 3 terms over here, and then I'm adding the 3 terms over here. The first thing I see is that the minus 2 cosine beta sine beta and plus 2 cosine beta sine beta, those look to me like they're just going to cancel, right? They're just going to cancel out. And then what we have is we have a sine squared beta, a cosine squared beta, a sine squared beta, and a cosine squared beta. And so what we're going to see when we combine is we have 2 sine squared beta plus 2 cosine squared beta. And then I could factor out the 2 if I wanted to. And then sine squared beta plus cosine squared beta, we're back to our original identity. This is just a big old fancy 1 right here. So that's just really 2 times 1, which is 2. Okay, so there's our third example. These Pythagorean identities, I can't say enough with identities. The more that you do, the better you get at them. But write those 3 identities down, use those, reference those over and over.